Thanks, Tully. So I don't know why I signed up for 2 talks. I'm really tired at this point. This ain't working. But I can't even really take credit for this project. Jorge Nicho, who's a research engineer at Southwest Research, is the primary developer. I just got lucky enough to come to ROSCon. So all the work is really Jorge deserves a lot of the credit. So. All right, well, we'll start with the application need. So Descartes is a path planner. I hinted at it in my previous talk, what it was for, and Dave Coleman actually did a good job of outlining what it's for, but we never talked about the applications. And in kind of a general abstract way, Descartes solves the problem of semi-constrained trajectories. But what does that really mean? It means that the degrees of freedom of your process or your path are less than the degrees of freedom that your robot provides. So you may have a 6 degree of freedom trajectory that you want to follow, but your robot has 7 joints. And this happens a lot with robots that have more than 6 joints, or even processes like machining or blending or painting, where the constraints are a little bit fuzzy. So maybe you have 5 degrees of freedom because you don't care about the roll about the tool. Or when you're painting, maybe a little bit of angle difference is okay because it's paint and who's going to notice, right? But those kind of semi-constraints really open up the planning space if you can utilize them. But that's not the case in traditional industrial robotics. So say you have a painting application, and you want to paint an object in front of you. How do you currently solve that problem? Well, there are definitely tools for doing this in the industrial space, but they all require you to make this arbitrary assignment of a 6 degree of freedom path, because that's all the industrial tools understand. If you have a redundant axis, so you have a 7-axis robot, you have to give it a 7th parameter that tells it generally where the elbows should be. But again, these should be free parameters. These shouldn't be things that you have to set. Also, by setting these things, you may actually get your robot in a weird spot, like near a singularity, where then the timing of your trajectory becomes suspect. And for things like painting, you actually want very good timing on your trajectory because that's what guarantees you'll get an even coat. But if you do the traditional approach, that may or may not be true. You may not be able to guarantee timing. So what are the limitations of the current solution, the traditional industrial solution? Well, first and foremost, you get reduced workspace. So if you look at the graphic there, the robot vendors will show you in their data sheets this really gigantic workspace. They'll talk about reach. My robot has a 1 meter reach. But that's really a 3 degree of freedom workspace because you can only reach that point in one orientation. And generally, that's not useful unless you're lucky enough to have to go to that point in that orientation. So when we reduce the workspace by imposing more constraints, so for example, a 6 degree of freedom workspace may look like what's pictured up there. All of a sudden, you take this really big reach and you kind of condense it down. And if the current solution really requires you to specify a 6 degree of freedom path, then really what the workspace looks like is what's pictured up there. Actually, I just kind of threw that visual in there. If anybody wants to work on a tool to actually produce visuals that show workspaces, that would be an awesome tool. But visually, that's kind of what it looks like. So when you're specifying these paths, you're relying a lot on human intuition. You want the human operator that's using these tools to essentially say, well, I'm going to set the orientation at this because that keeps my elbow out of the way and it won't run into things. But human intuition only goes so far. And certainly collisions, singularities, and joint limits, they really don't get accounted for in current solutions. But we know within ROS we can handle these things. All right, so what is Descartes? Well, it's a planning library for semi-constrained trajectories. In the software world, we like to say, do one thing and do it well, that typically means you're a new project and you can only do one thing traditionally. So that's probably more true about what we're doing now, but I'll take credit for it. We do one thing and we do it pretty well. We had some requirements. So again, generate these common sense paths that I was talking about. Find easy solutions fast, but we also want to solve the hard problems, but given enough time, right? So that seems tractable. We should be able to find that. Handle hybrid trajectories. So this idea that you have joint and Cartesian motion kind of interspersed. So you might define a joint point and then say, okay, from that point, I want to move in a straight line, right? So I have a bunch of Cartesian poses. That's real important because a lot of the tools within ROS either specify one or the other. You get all Cartesian points or all joint points, but you can't like mix them. But in real applications, you often do want to mix them. And then we had this additional requirement that we want to be able to do fast replanning or cached planning. So in a traditional OMPL move-it application, you solve a problem and you throw it out. We saw Dave Coleman's improvements where he would keep experience graphs so that he could solve similar problems or the same problem very quickly. This is kind of in that same vein, where if we made slight modifications to the trajectory via GUI or based on some sensor feedback, that would plan very quickly. So I'm going to start with an example. So the first example I gave in my talk this morning was blending, right? That used Descartes on the back end. But that wasn't the first application. The first application was what we call robotic routing. Essentially, it was using a robot to cut thin sheet metal into kind of very complex shapes. And the trajectory, the Cartesian trajectory that kind of defines what these shapes are, was either imported through CAD or you could actually measure it using a coordinate measurement machine. Didn't matter where the source was, as long as it came in, we'd be able to deal with it. So when we first did this, we had, so that path for a routing operation, as you might imagine, is a 5 degree of freedom path. But we had a 6 degree of freedom robot. So that meant we had at least one degree of freedom that we could play with. And when we first did this project, we solved an 800-point path in 30 seconds, which is not horribly fast, but for the project we were working on, it was good enough. It was kind of an offline programming. But we wanted to make it faster, and we did. Over the next several months, we got it down to between 1 and 10 seconds to solve that same problem. And we did that just by optimizing our code a little bit. It wasn't very difficult. We didn't actually have to change our approach. The path planner worked by minimizing joint motion. So typically, you got to have some cost, and that's just one that we've used, but you can imagine others. We achieved replanning, which was nearly instantaneous. We used this, in fact, to allow the user to modify paths via GUI. And then we had support for hybrid kinematic planning, right? So different waypoints, joint and Cartesian. And so here's just a quick video of Descartes and some of the features of it. So it says sneak peek because I showed this about 6 months ago, but it shows kind of the relevant capabilities. Oh, come on, don't do that to me. Oh, Windows. All right, I'm going to go back one, and I'm going to try it again. OK. That'll probably fail again. So what you see is, there's a YouTube link. If you go there, it'll work. But what we see is basically a Cartesian path and us solving it with an industrial manipulator using Descartes, and then giving the user the opportunity to go in and modify specific points. And when they go in and they modify those points, it replans instantaneously, and you can see the effect. So by kind of setting these anchor points in the GUI, you can actually get the robot to do what you want to do from a human interaction perspective. watch the YouTube video. I guarantee it's definitely worth it. It's exciting stuff. Path planning is awesome. It's really exciting. All right, so now to delve into a little bit of the details of what Descartes is. I don't get to do this too often, so like this is the perfect group to jump in and show what's under the hood. So what we did at first is we just defined the interfaces. What are the Descartes interfaces? There's a trajectory point, and this is completely robot independent, just defines some point in space. It can be fuzzy. It doesn't have to be any particular orientation, or it could have some bounds on its actual Cartesian position as well. And it includes some timing information, so that when you kind of piece these trajectory points together, you can then figure out the timing of the full trajectory. The second interface is a robot model, and we use this for IK and FK, forward kinematics. So kinematics are captured within the robot model. We use it to check validity, which for us includes checking for collision, joint limits, anything that might make the robot pose invalid. So this robot model is actually very similar to the MoveIt robot state, with the one addition, and if you guys are familiar with it, but it provides a lot of this collision checking and kinematics. But this one addition that we get all the IK solutions. This is important because if we're going to do this Cartesian planner and we're going to have to work through all the different kind of arm configurations a robot can be in, we have to know what those are. So that was the additional capability that we added to robot model. And then, a planner, which really just does trajectory solving, right? Give me a trajectory and I'll spit out a bunch of joint points that achieve that trajectory. And also handles the plan caching and replanning. Okay, so once we had that, we kind of had a structure for how all this stuff would work together. We hadn't actually implemented anything. So, it actually couldn't solve paths until we made implementations of these specific things. So in trajectory points, we define Cartesian points, joint points. Those are pretty straightforward. In a lot of our applications, we always have a Cartesian pose, but we don't care about the orientation about the tool. So that's what an axially symmetric point is. And I'm sure in the future we'll add a bunch more, but those are the three we've implemented so far. The robot model is really just the MoveIt wrapper. We use MoveIt kind of the back end for its environment model and kinematics capabilities. And we're actually working to take the extra things we need and push that stuff into MoveIt to make it a better user experience using Descartes and kind of move it together. You can also do fast IK wrappers. Dave introduced those this morning. Fast IK is really magic. It's one of the coolest things within MoveIt and OpenRave that actually implements it. The real benefit of it for us is I said we need to get all the IK solutions for a particular robot configuration. It provides those directly, and they're solved analytically, so they're very fast. When we don't have fast IK, we use KDL under MoveIt, and it's definitely a lot slower. And kind of our path planning approach, you want the speed. And then the other things we've done are kind of custom solutions where some really smart engineer figures out like the inverse kinematics directly. The planners that we've actually implemented are all graph-based. The reason we can get away with this is when you're dealing with a semi-constrained Cartesian trajectory, your search space is not that big. It's not like free space motion with MoveIt, where you go from A to B, and you could take any path to go from A to B. We've defined the path within some boundaries, and so it's a much smaller workspace. So we can just take traditional graph solving methods and throw them at this problem. And the first one we implemented, we called dense. So it's a graph-based approach, and it takes into account every point within the trajectory. And then the next one, we found by taking into account every point in the trajectory that sometimes you ran out of memory. So the next one was called sparse. We're great at naming, by the way. But it's a hybrid graph-based approach. So it uses kind of the dense planner underneath, but it also allows you to interpolate to points within the trajectory. So you don't have to load up the dense planner with all of your points. The result is, for most trajectories, it's much faster because interpolation is a faster search than graph-based search. So what does it really look like? What does an execution of Descartes look like? Well, at the top, you have a hybrid trajectory, right? The blue points are, well, they're blue up there, good. The blue points are joint points that you might define. The orange points are Cartesian points, right? And we have a certain order to them, how we want them to be executed. And then the size of the dot really represents, what's the tolerance on that particular point. So the larger the tolerance, the more joint solutions you might find for that because you have a bigger kind of zone you can get to. And so what we do is we take the hybrid trajectory and we do a sampling in joint space based on the tolerance, the collision, and what the kinematics tell us. And then, from that you may get multiple joint solutions for each one of these points. So as we move down the figure, you can see multiple joint solutions. And this is just our implementation of it. Nothing in Descartes actually requires this, but we do all graph-based search. So using that graph-based approach, we put all these points into a graph. They're all joint points at this point in the execution. We then calculate the connections between those points. And that's based on mostly dynamic constraints. So, two adjacent points in this graph are connected if the robot is physically capable of going from one to the other within the timing constraints. So you can imagine if you had to move your robot a very far distance in a very short period of time, that's not possible. We prune that out of the graph. And then we just throw graph solvers within Boost at this problem, and we come out with a cost-optimized path plan. And in almost all cases in Descartes, we just used the minimizing joint motion. So, some open source details. We do all this development publicly, which means we love to take contributions, but you can see the daily commits, you can see all the issues that we might have, and you can kind of see where the program or the project is going. We have documented things on the ROS wiki, so that's kind of a high-level description of how Descartes works. We have two releases, Hydro, which is our stable release at this point, and a binary release. And then we're doing all our development in Indigo. So for that reason, we haven't actually done a binary release of Indigo because we don't want people to use it and we know we're going to break their stuff. So we make it a source release, so at least you can fork the source and that will become stable. It would be really great. I brought this up this morning in the Move It talk, but it would be really great if we could simultaneously have a stable version of Descartes and an unstable version of Descartes. I don't know technically how that can all work, but if that could happen, I think we would be able to increase the number of users because it's far easier to get binary versions than it is to get source versions. We have a tutorial up there on how to use Descartes. It's pretty straightforward. And I'd like to acknowledge that the Descartes development was funded by NIST and the ROS Industrial Consortium FTP efforts. I will say that the Descartes demo, or we're demoing Descartes in our booth downstairs. We're using the UR5 robots, the one going like this. So it's following a 5 degree of freedom trajectory with a 6 degree of freedom robot, all planned using Descartes. Good? All right. So I think the question was, is the goal to integrate this into Move It, or why wasn't the Move It Cartesian path planner adequate for what we were doing? Is it? Okay.
So I guess at the moment it's not possible for the Move It API to just integrate this as an alternative add-on like
Yeah, so, yeah, I'm sorry. My apologies. So You're right, you can't call this through MoveIt. So most of MoveIt is pick and place. So going from A to B, so you give it a start point and an end point and nothing in between. So, but there was some kind of foresight into, we're probably going to want to define Cartesian paths, but they didn't support hybrid kind of Cartesian paths, at least not to my knowledge. I could be wrong. I'm sure somebody will tell me. But we developed it as a library, and then the ultimate goal is to push it into MoveIt. You know, we don't want to be kind of separate from everything. We want to integrate. So the question is, you know, these kind of interactive robots where you can grab the end effector and kind of walk it through the path. So I would say that once you've walked it through the path, you've done all the hard work, maybe. But you could use Descartes on the back end. You might record that trajectory, and then Descartes may optimize that trajectory for you. It's not a use case that we've actually worked on, but it'd be pretty easy to implement.